Okay, so part A is asking us to approximate r prime of 45. So instead of doing this with calculus, it just turns into a simple slope problem when you realize that there's a distinct value on the graph for 40 and a distinct value for 50, but there's not one for 45. So all you need to realize is that the derivative, r prime of 45, is just going to be the tangent line or the slope of the tangent line at r45. So you draw an r45 on the graph like I've done here, and then you see this tangent line. So that's the tangent line we're going to try to approximate. So we want to look to the table of values that our problem has given us, and we find that r40 equals 40 and r50 equals 55. So after this, it becomes a super simple slope problem. So we do delta y over delta x, or 55 minus 40, over 50 minus 40. And because the question asks us to indicate units of measure, we should add that on right now. So for y, it's gallons per minute, and then for x, it's just minutes. So we get 15 over 10, which gives us about 1.5 gallons per minute per minute. So one of the most important parts of this problem is the units of measure, and the way that we can double check that we got these correctly is because we know that if we derived gallons per minute, we would get gallons per minute or gallons per minute squared. A different way to think of this is that when we derive velocity, we get acceleration. So a standard unit of velocity can be meters per second, and we would derive that, and we would get meters per second or meters per second squared. So part B of question 3 is actually going to be pretty similar to part A, and that's just asking us again to approximate a value of one of the derivative graphs of r of t. So because it said r prime of 45, I decided first to try to draw out the graphs of r prime of t and r double prime of t. However, because there aren't many values they give us to work with, it turned out to be pretty difficult to graph. So then I went back to the question and I reread it and found that I had missed something huge. So the question asks, the rate of fuel consumption is increasing fastest at t of 45 minutes, and then it asks us to approximate this. So what I had ultimately missed is that it said it's increasing the fastest here. So because it's a rate, that means that r prime of t, not r of t, is going to have a maximum value here. So because r prime of t has a maximum here, when we derive that, we're going to get the slope, and because a slope at a maximum or minimum is always 0, we find that r double prime of 45 equals 0. And so because it asks you to explain your reasoning, it's just exactly what I said. You say that because r prime of t has a maximum value here, r double prime of 45 equals 0. So part C of this question is just asking us to estimate the integral of r of t from 0 to 90. So normally, because this is a graphing calculator problem, we would just go straight to our calculator and plug in this function, right? But because it doesn't give us a definite function, we have to look back to the graph, and it asks us to use a left-hand Riemman approximation with 5 subintervals. So what I like to do for Riemman approximations is draw in the rectangles that I'm going to use, just to help me visualize later on. So I'm going to draw these in right now. And it asks us to do a left-hand approximation, which means that we're going to begin our heights of the rectangle from the left side. So if you draw in the tops, it's just going to look like this. And then when you shade it in, you're going to find that the values are underneath the graph. So then this is the time when we would look back to our functions, or the table of values that our question has given us, and then we're just going to estimate really simply these rectangles. So I've plugged it into my calculator already. So what I'm doing is I'm just multiplying really the basic area of a rectangle. So here, the way that you're going to estimate the values of the rectangles is you're going to look back at our original function, and you're going to look at the intervals between each of the points. So between the first and second point, there are 30 minutes that passed. Between the second and third, there are 10 minutes that passed, and onward. So you just want to look at these rectangles, and you're going to use the base as the minutes, and then you're going to use the height as r of t. So you're going to look up here, and because it's a left-hand approximation, you're going to take the left point. So if I'm looking at a rectangle that has the first and second value, you're going to take 20, because that's the left-sided dot. That's the one we're going to use for the height. And so this rectangle right here is going to be a 30 by 20 rectangle. So you're going to keep doing this with all of the rectangles, and at the end you're going to add them up on your calculator, and this is going to give you your Riemman approximation from the left side with the 5 subintervals. And as you can see, there are 5 subintervals because I've used 5 rectangles to estimate this area. And then I plugged it into my calculator, and when you add all of those rectangles together, you get 3,700. So if we're using our left-hand Riemman approximations with the 5 subintervals like it asked us, that is going to be our approximation here. So the second part of this question is asking us to determine whether this is an over or under approximation of the actual value of r of t from 0 to 90. So like I've shown you before, when I draw on these rectangles, you can obviously see that it's going to be an under approximation because all of the areas fall short of the curve, but they want a better answer to explain this. So part of the definition of Riemann sums is that if you have a function f of x that is increasing and you use a left-hand approximation with a Riemann sum, it's always going to be an underestimate. That's just part of the definition, and you can also see why, because if you have any increasing function and you use these values again, when you estimate from the left side, it's always going to fall under the curve, no matter what function you have. For the second part of part C, we would say that you would just have to say this is an underestimate because r of t is increasing, and you would want to say over the interval which it is increasing, which is 0, t to 90. And that's all you really need to do for both parts of the question for part C. So finally we get to part D of this question, which is asking us to give the meanings of these two integrals. So the first part of this question is just asking you really simply to define what this integral means, which should look pretty similar to what we did in part C already. So the integral of RT from 0 minutes to b minutes essentially means that you're integrating the original rate we have in the problem, which is gallons per minute. So any time that you integrate a rate, you're going to get out a numerical value or like a concrete substance. So basically you're going to get out gallons here. So when we're integrating this, it just means that the gallons of fuel consumed by the airplane from 0 minutes to b minutes during the flight. So that's a pretty straightforward, simple one. And then we get to the second part of the problem, which is pretty much the same part as the first problem, but now we have the 1 over b. So if you know the average value theorem of calculus, it basically says that a function, let's say f of x, integral of this over b minus a is the average value of the integral from these limits. So what we have here is the gallons from 0 to b minutes, but then we have 1 over b. And since we know that b and 0 are time, you basically have 1 over time times gallons, or times gallons per minute. And so once again, when we integrate gallons per minute, we're just going to get gallons. So you basically have 1 over time times gallons, which just once again gives you gallons per time or gallons per minute. So all that the second part of this question signifies is the average rate at which this airplane is consuming fuel. So whenever you have a 1, b minus a, let's just say a is 0 here, out in front of the integral, it's just going to be the average value. So here, for our explanation, it would be the average rate at which fuel is consumed from 0 to b minutes. So what we've covered in this problem is basically in part A, we're just doing linear approximations using these values given. And in part B, we basically did the same thing, but we defined it at the second derivative. And then in part C, we went over some Riemann sums and then what the meaning of this is. And we also went over how to approximate Riemann sums if they're over or under approximations. And then part D asked us really to define the basic fundamental meaning of an integral and then the average value theorem for integrals, which is super important. So all of these things, I have more materials if you would like to try out more problems like this. They will be linked below, and you can go to the College Board website and I'll have some example FRQs that are pretty similar to this, covering any of these topics listed. So I really hope this was helpful.